So far in the course, we've been discussing the ray picture, which is sort of like a geometrical optics picture, right? And as you know, that's only an approximation, right? Specifically for waveguides and fibers, like the things we've been discussing, they are valid only for highly multimode waveguides or fibers, right? This ray optics picture that we've been discussing. And as you know, the actual sort of behavior of light is described by a wave picture, right? Where we solve the Maxwell's equations. And so that's what we'll start today, right? So we'll look at the modes in a planar slab waveguide. So we'll get into more of what we exactly mean by a mode, okay? But it's basically the pattern of electric and magnetic field associated with the optical field which travels along the waveguide, right? So we'll be looking at a symmetric planar waveguide to start with, because of course, I mean, in the course we are sort of primarily interested in fibers, but a lot of the basic concepts can be understood with this planar waveguide, which is easier to solve because it's in Cartesian coordinates, right? So after we sort of understand modes in the planar waveguide, we'll move on to the actual fiber, which is cylindrically symmetric or in cylindrical coordinates. So as you know, we already introduced this planar waveguide, right? So let's say the vertical coordinate is x, and then the this propagation direction that we'll be looking at for the wave is the z direction, and the structure is infinite, extends infinitely in the y direction. Right? So it looks like a slab where the core has some refractive index n1 and the cladding has some refractive index n2. Right, so to begin with, we'll look at a step index waveguide where the refractive index in the core is constant. So later we'll also look at a gradient index one where, for example, the core index has a parabolic profile. But to begin with, we'll look at a step index. Right, and let's say the extent, so the thickness of this slab is b. So this is it extends from minus d by 2 to d by 2, and x equals 0 is the sort of symmetry plane. Right, it's called a symmetric planar waveguide because the structure is sort of symmetric about x equals 0. Right? Because the refractive index here in the top cladding and the bottom cladding is the same. We could also have asymmetric planar waveguides where the refractive index and the top cladding and the bottom cladding is different. Okay. But we won't look at that because for our purposes, like for example in fibers, the cladding surrounding the core has the same refractive index. Right? So the important concepts we can get from studying this symmetric waveguide. Right, so this is step. Okay, so basically the idea would be to solve the wave equation in this kind of structure, right? And so we'll use some boundary conditions like these boundaries, right? And look for a solution which is sort of invariant as it propagates along z, right? So the only thing that the wave should acquire is a phase shift as it propagates along z, right? So for example, in free space, you know, like plane waves, right? They just acquire a phase shift as they travel along the propagation direction, right? So basically a mode is some transverse, so in the xy plane some mode like field distribution for E and H that remains the same as it propagates, right? And the only thing that happens is as we propagate in Z, there is a phase shift acquired proportional to the distance z, like e to the I k z kind of thing, right? But the transverse field distribution or the intensity distribution remains the same, right? So that is what this will mean by modes. So let's consider a monochromatic wave at a particular frequency, right? So, so as a function of position and time, we will write it as a monochromatic wave e to the I omega t. Okay? So at each particular frequency, we get, as you change the frequency, the mode will change, right? So we are solving at a particular frequency or a particular wavelength. And the position dependence we've taken here as a function of x and z, right? So we have not taken any y dependence because the structure is invariant in y, right? So it just extends infinitely in y. So because of this translational symmetry, right? So I can move this, I can solve this at some particular y or some other particular y or a different y. It all looks the same, right? So there is no y dependence because there is no way for me to distinguish different y coordinates. Okay? So that's why we don't take any time. Right? If there was some structure in the y direction also, right? So for example, if you had a 2D waveguide, right, which has, so for example, it looks something like this, right? So, right, so there is some structuring like this, and then the waveguide extends into the z direction. Then we'll have to take x, y, depending on y also. But here, since there is no change in the structure along the y direction, we can just sort of say that there is no y. Okay, so similarly, the H magnetic field will also look like this, right? And we want to solve for these functions, basically. Right? Those are the modes. And now, so by construction, we also take a wave which is propagating in the z direction, right? So as I said, that means that we look for something that acquires a phase shift as it propagates in the z direction. So this E of x comma z, we'll write it as E of x, and the z dependence is just a phase shift. Okay. We'll take that as e to the minus I beta z. So beta here is the propagation constant, which is basically the equivalent of the wave vector, right? So the k that we have for plane waves in free space, for example, this is something like that in a waveguide. Okay. So this is called, so we'll see what this actually is, right? So this will depend on, for example, the wavelength and also the waveguide parameters. So we'll see how that comes about. Right, so in free space, for example, it just depends on frequency, right? And or in a homogeneous medium, it just depends on frequency and the refractive index, k is omega over c times n. So here, because the refractive index is not constant, right, there is some change. So you can't just write k like that. Okay? So this beta we'll see how it depends on the structure. Right. So another way of looking at it is that each particular mode. So for a particular frequency, you'll get a particular field profile and a particular beta. So if I change the wavelength, the beta will change, the mode profile will change. Right, so this is the propagation constant, and this is basically the mode profile, right? The electric field distribution with position that remains invariant as the field propagates along with it. Okay, so the first thing we'll sort of note here is that for any kind of waveguide structure where you have variation in the refractive index, right? So guided waves cannot be TEM, right? Right. So, for example, in free space, we know that plane wave solutions are actually TEM, right? Transverse electromagnetic, which means the electric and magnetic fields are both perpendicular to the propagation direction. But as soon as you have some structuring and guidance of waves in a particular structure, we'll see that you cannot have purely TEM waves. Okay? Which means that either Ez, right, which is, so Z is the propagation direction, so the electric field along the propagation direction or the magnetic field, one of these has to be non-zero. Right? For purely TEM waves, both of these are zero. There is no longitudinal component. Okay, so in this structure, we'll see that we can either have TE modes or TM modes, but not TEM modes. Okay, so TE means the electric field will be transverse to the propagation direction, but the magnetic field will not be, right? So in TE case, Hz will be non-zero, and for TM, Ez will be non-zero. Okay, and this is true for any type of waveguide. As soon as you have some structuring like change in refractive index and some waveguiding, this particular thing has to be satisfied. You cannot have purity inputs. Okay, and that just comes from the Maxwell's equations, because the Maxwell's equation and the boundary conditions that lead to satisfy. Okay, so for example, like for TE modes, so if I consider TE modes, then this mode profile, right, E of x, we'll say it's pointing in the y direction, right? So perpendicular to the board. So that's so the electric field vector perpendicular to the board is perpendicular to z. Okay, so the electric field is transverse, right? But now if you use the Maxwell's equations, so we use del cross E right? So starting from this, you can use this Maxwell's equation to get H, right? So when E and H are of this form, right? So if I also write like this, so E and H are of this form. Right, so this phase part looks like a plane wave, right? Omega t minus kz kind of thing. Except now you have here, instead of a constant, you have a position dependent field, which is the mode profile. Right, so if we plug these things into the Maxwell's equation here, right, and for E of x we take something only pointing in the y direction. Right, so if E is pointing in the y direction, then del cross E will have components in the x and z direction, right? So, for example, if you take the x component of this equation, right, so that will depend on del Ey by del z, right? And what is del Ey by del z? Right, so so the only z dependence here is this e to the I beta z phase factor, right? So when we take the derivative with respect to z, we get this minus I beta out in front, right? So basically, with the x component, we get I beta times Ey, and then here we have a time derivative, and the time derivative you can see we'll just take this I omega out front because that's the only time dependence. and h of x because we're taking the x component. Okay, so you can see that the magnetic field will have an x component proportional to the electric field which we've taken in the y direction, right? So the amplitude, so this is also a function of x, right? Right, so that's how the magnetic field in the x direction depends on the electric, right? But also this will have a z component. So if you take the z component, right, so that will depend on del Ey by del x, right? And del Ey by del x now will be the derivative of this part, right? Because that is the x dependence here. And here again, on the right hand side, we just get I omega because the time derivative, and then the z component means the z component of the magnetic field. Right, so you can see that so Ey of x is some smoothly varying function, right? So we'll see what exactly that is. So this derivative is also another smoothly varying function. So Hz is non-zero, right? So from here, okay. So you can see for TE modes, basically the non-zero field components are Ey, Hx, and Hz. Right, because so there is a z component of the magnetic field, it's called TE. So electric field is transverse, but magnetic field is not. Right, by the same analogy, you can see that for TM modes, what we'll say is the magnetic field is transverse, like that. Right, and for TM modes, you'll see that so now Hy, Ex, and Ez are non-zero. Right, so for TE modes, these three field components exist. These three field components are zero, and for TM modes, these three field components exist. These three are zero. Okay, and we'll see that TE and TM modes have slightly different properties. Right, so for example, at the same frequency here, the TE and TM modes will have slightly different propagation constants. Okay, so for TM mode specifically, like you have to use the other Maxwell's equation, right? So del cross H, because we assume an H. So we have del D by del T on the right hand side, which we can write as epsilon times E, right? Epsilon is epsilon naught times the dielectric constant, which is the square of the refractive index. Right, so again you take the x and z components, you see that, so Ex I can write as this constant times, or this value times Hy, and Ez I can write will not depend on the derivative of Hy with x. Okay. So I hope that's clear. So now, basically the task is to individually take, so we take TE modes first, and then solve the wave equation and try to find what exactly this Ey of x is, right? So how the mode profile looks, and then find out how to calculate beta for a particular mode, okay? And how that varies and different properties, right? And then we'll see how the TM modes compare with TE modes. So let's start with TE modes. Right, so try to think about why we couldn't make the same. So our argument about that we can't have TEM and only TE or TM was just based on the Maxwell equation, right? So you might think, why can't we make the same argument for example, plane waves in free space, right? Right, but there we have TEM waves. Why can't we make the same argument? Because we just use the Maxwell's equation. So think about that. Okay, so yeah, so let's start with TE modes. Right, so the electric field we can write like this, pointing in the y direction, function of x, and then the phase dependence is like that. Right, and so now, so if we consider this step index waveguide, if you look just in the core or just in the cladding, it's a homogeneous medium, right? Overall, it's an inhomogeneous medium, but if you just look in the core or in the cladding, it's a homogeneous medium there. So basically, we can individually write, solve for the homogeneous wave equation in the core and in the cladding, and then use boundary conditions. Okay? So recall that we derive this homogeneous wave equation, right? Right. So for a medium with constant diffractive index, we satisfy this. Right. So we basically plug this solution for E into this equation. So now the del square. So again, we can see that there is no y dependence here, right? So first of all, instead of, so usually we have three components or three different scalar equations, right? One for Ex, one for Ey, one for Ez. But here we can see that we have only Ey, so we have only one equation for Ey, right? And then also the dependence is only on X and Z, right? So del square here will only have the X and Z terms, no Y term, right? And the Z term, right, again, is just a phase, right? So del by del Z is just minus I beta. So second derivative will be square of that, right? So this will just give me a factor of minus beta square. Similarly, the time derivative here, right, is just again the phase. So double derivative will give me square of that. So again, this just gives me a factor of minus omega square. Right. So doing that, we get this equation for Ey. Okay, so omega by c is the free space wave vector, right? Which we define as k naught, which is basically 2 pi by the wavelength, right? The free space wavelength. So basically, we write this like Okay, so we get this equation for Ey. So it's a second order differential equation. Right, so in the core, n will be equal to n1, and in the cladding, n will be equal to n2. Right, so this n here, n1 for mod x less than d by 2, right, in the core, and n2 right. So basically, we have two different equations, one in the core, or you can even say three different equations, one here, one here, one here, right? But these two are sort of the same, just right? So we'll solve individually in these regions and then use boundary conditions. Okay, so the first thing to see is that the kind of solutions we want is that as x goes to plus infinity or minus infinity, right, so far away from the core, the field should eventually decay to 0, right? So we want some guided mode which has a finite, right? So, and physically relevant solution would be like the ones which eventually decay to 0 far away from this, right? So we want solutions which decay. Right, so first thing to see, so if I assume this to be some constant here, right, depending on the value of n, then you can see that, so either this could be positive or negative. So if this is positive, right, so that's second derivative of Ey is some constant times Ey. For a positive constant, you know that the solutions are sinusoidal, right, or complex exponentials. Right? Or if this constant is negative, then they are pure exponentials. Right? So either increasing exponential or decreasing exponential. Right? So basically from this equation we already know that the solutions have to be some exponential functions, either complex exponential corresponding to sinusoidal function, like sine or cos, or a real exponential function, right? So the solutions are either like e to the I some alpha x, right, plus minus, or like if this constant is positive, then the solutions are like that. If this constant is negative, then the solution is something like that, right, plus minus alpha x. So basically, we know that it could. So if it's in the cladding, if it's a solution like that, then we know that this is a sinusoidally varying quantity, which as x goes to infinity, it's still finite, right? It just keeps oscillating. So this kind of solution is not possible in the cladding if you want a guided mode, right? So this kind of thing will be like a propagating mode in the cladding, right? Something which travels into the cladding forever. But that's not a guided mode, right? That's a thing which leaks out. So this kind of solution is not what we are looking for in the cladding. So in the cladding, the solution has to be something like this, either increasing or decreasing exponential, but then we want the field to decay to 0 eventually, right? So they have to be decaying exponentials. Right, so from that, so basically, Ey as x goes to plus minus infinity should go to 0. So this implies that basically this constant in the cladding has to be negative, right, to get an real exponential solution, which again is decaying, is what we choose, but we can't have this type of solution, so this has to be negative, which means you can see from here, so beta has to be greater than k naught n in the cladding, so k naught n2. Okay, so that's one condition on beta that you already have. Okay, and then we need to satisfy boundary conditions here at the interface, right? So in the core region, we'll have these kind of solutions, okay? And basically that comes about because of the boundary conditions. So if you want to, so what are the boundary conditions, right? So that EY and HZ. So these are the tangential components. So if you look at the surface here, so let's say look at the surface x equal to d by 2. EY is tangential and HZ is also tangential. And tangential components have to be continuous. So EY and HZ basically are continuous at x equal to plus minus d by 2. Right? So basically the solutions of cladding and the core have to match at x equal to d by 2 for EY and HZ. And we just erased it, but for TE modes, we saw that HZ is something proportional to the derivative of EY and HZ. Right? So this condition is equivalent to saying EY, and then the derivative of EY with respect to x have to be continuous. Right? And you can again check that for these kind of solutions, right? If you want to satisfy these boundary conditions, then beta has to be less than K naught N. Okay. So you can see that you can check yourselves that if beta naught becomes greater than K naught N1, then these cannot be satisfied. Okay, so again, I take solutions of this form and then try to match them here. You'll see that. Okay, so in this case, if beta became less than K naught N2, then field sort of leaks into cladding and travels away, right? So these are also sometimes called radiation modes. So they are not guided modes, they are radiated away, right? So we are not interested in them anyway. So for beta less than K naught. And then for beta greater than K naught N1, the boundary conditions cannot be satisfied. So that means that beta has to lie in this range between the core and cladding refractive indices times the free space wave vector. Okay, or I can write it like this. Right, so this looks familiar, right? Recall that when we were discussing these ray paths, right, again, in these types of waveguides, we saw that, so we had defined this parameter beta tilde, which depended on sort of the launch angle for the ray, right? And we saw that the rays would be guided if beta tilde lies between N2 and N1, right? If it's, we saw the same thing that if it's less than N2, it will like leak away. So this beta over K naught is something equivalent to this beta tilde, right? So beta tilde in the ray picture denoted sort of the angle that the ray makes with the axis, right? So this beta propagation constant normalized to the free space wave vector is the analog of that in wave optics. Okay, so we'll see also like a more precise analogy also later, right? So from here you can sort of think of these different modes as waves traveling the core at different angles to the propagation axis, right? From this analogy. But yeah, we'll see more about that later also. But anyway, so for physically relevant solutions, beta has to lie in this range. Okay, so when the equations are that, so in the code we have these kind of equations, right? So this constant is positive. Right? So kappa here is square root of k naught n1 square minus beta square. And then in the cladding, this constant flips sign. Right? So gamma here is square root of beta square minus k naught n2 square. And immediately we know, so these are again solutions here are like e to the I plus minus kappa x or sine kx cos kx, while here it's e to the I, so e to the I minus gamma in the positive direction and e to the I plus, sorry, e to the minus gamma x for positive x and e to the plus gamma x for negative x, so that the field is decay to 0. Right, so I can write the solutions like this. So superpositions, let's say sine and cosine in the core. Okay, and then exponential in the class. And so basically to find these constants or relate these constants A, B, C, D to each other, we'll use the boundary conditions, right? So we have 4 constants here, A, B, C, D, right? So one of the constants will depend on basically the, right? So there is one constant which just decides the amplitude of the field, right? Which depends on the power in the waveguide that we launch. So that one constant will be sort of a free parameter, like one constant which depends on the power we launch. But the other 3 constants would depend on that, and the solution should just finally depend on the parameters of the waveguide. And so how many boundary conditions we have? So we have 2 boundary conditions for each boundary. So that's 4 boundary conditions in total, right? So we have 4 equations. We get 4 equations from these, right? So Ey and del Ey by del x continues at x equal to d by 2 and minus d by 2. So we get 4 equations, right? So we have 4 unknowns here. Actually, we have 5 unknowns, right? Because beta is unknown, right? And so gamma and kappa just depend on beta. So once we know beta, we know gamma and kappa, right? So gamma and kappa that appear here are just functions of beta. So A, B, C, D, and then beta is the 5th unknown. So we have 4 equations. So you can see that out of the 5, we'll just be left with 1 unknown, which is sort of the electric field amplitude. Others will be determined from. Okay, so we can sort of simplify the form of these solutions a little bit more by first recognizing the symmetry of the medium. Right, so again, it's a symmetric planar waveguide, which means like there is mirror symmetry about x equal to 0, right? I just erase the, maybe I should write it again. So the wave equation, homogeneous wave equation is something like this. Or if I take the omega, then it's just a constant here, right? Right, so that's a homogeneous wave equation. So if we take a medium as a whole, this is some function of x here, right? The refractive index. So if you have some symmetry like this, so for example here, we know that x and minus x have the same refractive index, right? Both for the core and cladding. So as a whole, the refractive index satisfies this symmetry. So if you have this symmetry, then in this equation, the solution Ex, okay, will satisfy this symmetry, that it has to be either odd or even. Okay, so basically you can take this equation, then take x to minus x, okay, and then you'll see that like there's another equation you get, and then doing some transformation, you can see that if this is satisfied, that if e of minus s is equal to x or minus of e of x, so it's either odd or even, then the equation is satisfied. Okay, so okay, this means that the electric field profile is either even or odd. Okay, so you might have seen this, I don't know, in some other courses also, like for example, a basic quantum mechanics course where we try to solve the Schrodinger equation for some potential. Similar, you get a similar equation, and then again, if the potential is symmetric, then we assume even or odd solution. Right? Like for example, in a square potential well, or like a simple harmonic oscillator, like a parabolic potential, the solution satisfies this being even or odd. So as long as you have the symmetry, right? So we can individually look for either even solutions or odd solutions, right? Which means here we can either look for, so even solutions would be cosine kappa x, right? Even functions, and odd solutions will be sine. So we can separately look for solutions where either A is 0 or B is 0. Those would correspond to different modes. Okay, so for even, they are called the symmetric TE modes. Right, so they satisfy basically Ey of x is equal to Ey of minus x, even functions, right? Right, so now let's use boundary conditions again. Okay, so boundary conditions. So Ey at d by 2 sort of from coming from the core to d by 2 minus has to be equal to the solution in the cladding also at d by 2, right, coming from the cladding, so d by 2 plus. So basically we have to put x equal to d by 2 here and x equal to d by 2 here and equate. So that's one equation we get, and then from the second boundary condition is that the derivative of Ey also has to be continuous. Right, so from that we get okay, so we have these two equations. So what we can do is just divide them to eliminate this A's and C's. Okay, so you'll see that so when you divide, so divide 2 by 1. So 2 by 1. So you get a tan here, right? So basically we can write the equation that we get like this. So the equation that we get, we can write like this. So, right, so this is the equation we'll get, kappa d by 2 times tan of kappa d by 2, this is gamma d by 2. Right, so this kappa d by 2 we denote by this symbol zeta, I guess, or zeta, I don't know, sorry. Right, and this, so again, recall, so this was kappa and this was gamma. Right, so if you do kappa square plus gamma square, so this constant on the right hand side will write as this constant V, okay, where V is k naught d square root of n1 square minus k. Okay. So what are we saying? So kappa d by 2 whole square plus gamma d by 2 whole square is basically V by 2 square. Right, you can check from here. Right, so this is denoted as a V number of the waveguide. Okay, so you can see this constant is just depends on waveguide parameters. Right, d is the thickness of the slab, n1 and n2 are the refractive indices, k naught is 2 pi by lambda, which is sort of the wavelength of the mode, that is again sort of a parameter under our control, right? And then this kappa and gamma depend on the solution beta. Okay, so basically if you solve this equation, right, so the equation that you get here is okay. So this is a transcendental equation, right, in zeta. Right, so if you solve this equation, you basically get a solution for zeta, right? And zeta is basically this kappa d by 2, so kappa depends on beta. So the only unknown is beta, right? So once you have a solution for beta, that corresponds to a value for beta, the propagation constant, okay? So this is known as the transcendental equation for symmetric TE modes, right? Right, now we can again take the anti-symmetric modes. So for anti-symmetric mode, now it's an odd function, right? So which means here we assume a sine solution. Okay, and then here, this is an even function now. So, sorry, odd function now. So there's a sign of x here. And let's call this d because okay. So that would be the anti-symmetric modes. And again, we can do the same thing, right? Boundary condition. So you'll see that you sort of get like a sine here, right? And this will become cosine here. Right, so when you divide the two equations, you get cot instead of tan, and you get a minus sign here because the derivative of sine is plus cos, but the derivative of cos is minus sine. So you get a minus sign. So again, we can write it in terms of this same parameters zeta and b. So you can see that the equations that you will get, the transcendental equations you get for the antisymmetric mode, will be, so you get a minus sign and then tan becomes cot. Okay, so this is the for anti-symmetric TE mode. Okay, so it satisfies a different equation, so you can see it will get a different beta, right, for the same wavelength or frequency, right, and for the same V number, so for the same waveguide. Okay, so how do we, so there's no analytical solution to this, these kind of transcendental equations, right? So either you solve it numerically on a computer, or we can get some idea by looking at just graphically, looking at the solutions. Right, so this right hand side, so what we'll do graphically is, so the left hand side is a function of zeta, the right hand side is a function of zeta. Okay, so we can plot on the y-axis a function of zeta, and on the z-axis is zeta. Right? So on the y-axis, we can plot the LHS and the RHS separately. Right? So this is f1 of zeta, this is f2 of zeta. We plot both of them and then look for the intersection. Right. So this right hand side, square root of some constant minus zeta square. Right. So that basically is the equation of a circle. Right. So this looks like y is equal to square root of some r square minus x square, which is basically the x square plus y square equal to r square, which is the circle. Right. So this is the equation of a circle with radius v by 2. Right. So that's the right hand side. So if in the positive quadrant, we'll get like a quarter circle like this. Right. So as I increase v, I'll get circles of increasing radius. And then we have tan and cot functions, right? So it's multiplied by zeta again, but basically the variation of tan and cot is, you know, very sharp, right? So basically the variation will look similar to that. Okay. So this is pi by 2, right? Here. At pi by 2, this function blows up. Right, and then it starts from negative again here, but we don't look for negative solutions because the right hand side is positive, so we want only positive. So then again it starts from here and then goes like that. This is pi, 3 pi by 2, 2 pi. So these solid lines are basically the tan function, zeta times tan zeta. That's what these lines are. So again, it will start again from here. And then this chord function will occupy the other region. So if I draw a dotted line here, so this dotted line would be the cotangent. Okay, so the solid lines correspond to this for the symmetric TE modes, and the dotted lines correspond to this for the anti-symmetric, right? And then the right hand side, as I said, is a circle, right? So for example, V by 2 is the radius, right? So if I take V by 2 equal to 2, right? So that will be somewhere here. Pi by 2 is like 1.7, so 2 is somewhere here. So that's a circle of radius 2, right? So I draw it like that. So this is for V by 2 equal to 2 or V equal to 4, right? So you can see that it intersects the psi tan psi here once, right? So that will correspond to a symmetric TE mode, right? So this is some solution zeta naught, which corresponds to the symmetric TE mode, and then there is another intersection here with the dotted line, which is the cotangent function that corresponds to the anti-symmetric mode. So this solution, let's call it some zeta 1, right? So zeta 0 corresponds to the symmetric TE mode, right? So this subscript I've denoted 0 for a reason. So this is called the TE 0 mode, and this would be the TE 1 mode. Okay, so the subscript, if it's even, then it's a symmetric TE mode. If it's odd, then it's an anti-symmetric mode. Okay? So for V equal to 2, V equal to 4, we see that we get only 2 intersections, right? So 2 modes, right? If I increase V, so let's say I make V equal to 10, for example. So V by 2 is 5. So 2 pi is 6 here, so it's somewhere here, right? Somewhere here. This is 5. So now I get a circle of radius 5, like that. Right, so this is V equal to 10. So now you can see I have more intersections, right? So this is one intersection here, so that again T is 0. Then the next intersection with the chord here, that's TE1. Now I have another intersection with the next tan, so that's TE2. And then with the next cotangent one, that will be TE3. Okay. So now I have 4 modes here for V equal to 10. 2 symmetric modes, TE0 and TE2. 2 anti-symmetric, TE1 and TE3. Okay. So all of them have different zetas, which means all of them have different betas. Okay. For the same frequency, we have different betas. Okay. And since beta determines kappa, and then the kappa, like cosine kappa or sine kappa X defines the field profile, they also have different field profiles. Right? It's just that the even ones have even symmetry and odd have odd symmetry. Right? So if you plot, right, so this subscript here also denotes sort of the number of zeros you have in your mode profile. So if you plot, right, so TE0, so it's a cosine function, so it will look like that, right, in the code, like a cosine function. And then in the cladding, it will be exponentially decaying. Okay, so it will look like that. And T0 means there will be no zeros in the mode profile. Now you go to TE1, so now it looks like a sine function, so it looks like this, right? So odd symmetry, and again exponentially decaying in the cladding. This is TE1, right? And so on. So TE2, again we have even symmetry, so it's cos, but then it will have 2 zeros here. Okay, 1 0 here, 1 0 here. and then again exponentially decay. This is TE2, right? So you can see. Right, so what is happening here? So you can see that for the higher modes, as the m, so T sub m, as the m increases, the zeta for that mode is increasing. So zeta is basically just kappa, right? So kappa is increasing, and you know the mode in the core is, so for the even one it's cosine kappa x, right? So as you increase kappa, the period goes down, right? So it shrinks. So that's why T0 has a longer period because kappa is smaller, right? So kappa x, so 2 pi by kappa will give me the sort of the period of this sinusoidal wave here. So this is smaller kappa, this is larger kappa. So you have more oscillations within the V as the mode number increases. Similarly for this line, and similarly for gamma, okay? So basically for higher, what's happening as the mode number increases is that kappa is increasing, which means beta is decreasing, which means gamma is also decreasing, right? And gamma decreasing means this exponential decay is slower, right? Because e to the minus gamma x. So higher order modes leak or penetrate more into the cladding. So if you're looking, for example, at what is the confinement factor, what is the percentage of the power in the core, that's maximum for the lowest order mode, then for the next. As the mode number increases, more and more power goes into the cladding, right? And you can see that for a particular V number, there is a finite set of modes, right? So here for V through 10, we get 4 modes, right? So the power in the cladding increases, and beyond a point, it's not guided anymore. Okay. So you can see basically that if this V number, right, if it's greater than m times pi, then the TEM mode exists. Right? So if it's greater, so the TE0 mode will always exist, right? Because this curve starts from 0. You can decrease V as much as you want, you'll always get an intersection, right? So V is basically depends on the film thickness and the wavelength. So either, let's say you keep decreasing the thickness, or you keep decreasing the index contrast, or you keep increasing the wavelength, right? So that reduces the V number. But no matter how small you make it, you always have this first. So TE0 mode is always guided, right? No matter how thin this is or how small the index contrast, right? But the next mode will only exist if V is greater than, So next, if this radius, which is V by 2, is greater than pi by 2, right? So if it's here, V by 2 is less than pi by 2, you don't have the next mode. The next mode only shows up when the radius becomes more than pi by 2, right? So, and you can extend the same argument to the next mode, right? So as V by 2 increases by pi by 2 every time, you introduce a next mode. Or equally, when you increase V by pi, you introduce another mode. So basically, if this V is greater than m pi, then TEM mode exists. Right? So if it's less than m plus 1 pi, then TEM plus 1 mode exists. Right? So by just looking at this V number, you can say how many TE modes exist in the structure. Right? You can see in which m to m plus 1 pi it lies, and then you can say there are m modes.